700 gallons to refine a barrel of petroleum, 2,500 gallons to provide a pound of beef, and more than 40,000 gallons to build one automobile. But as impressive as these figures are, the importance of water is perhaps best revealed by this fact. More than 60% of every human body is H2O. "2,500 years ago, Thales of Miletus, the father of Greek philosophy, taught that the earth was sustained by water. As we now know, his premise was quite accurate. But what is it that really makes this priceless resource so unique and vital? Throughout both nature and the laboratories of science, the answers abound. It has long been recognized that water is the most remarkable solvent on Earth. To demonstrate this ability, more than a cup of sugar is poured into a beaker already filled to the brim with water. Surprisingly, instead of overflowing, the liquid totally dissolves the sugar without affecting the water level. Given enough time, water will dissolve almost any other substance. Its significance as the universal solvent is graphically displayed in the process of erosion. Every time a water drop falls to Earth, it dissolves and collects molecules of chemicals, nutrients, and minerals. In fact, nearly half of the world's known elements are found in its waters. Without this ongoing process of collection, the Earth's land-based plant life would cease to exist. For only as nutrients are dissolved in water can they be absorbed and consumed by the vegetation of our planet. Yet through erosion, water's work as an agent of collection and supply is only partially complete. After the chemicals and minerals are dissolved, they must be transported to the food-producing structures of a plant. A trip into space reveals some unexpected clues into how this task is accomplished.
One of the fun things to do when we're up in space in a weightless environment, in zero gravity, is to play with your food, particularly the liquids. And water up in space doesn't flow because there's no gravity to cause it to do that. Instead, it forms a little bubble whenever you put your lips up on it and try to suck it in. If it's of any size at all, instead of all just coming in your mouth, it'll kind of stick all over your face and get up your nose and cause you to spit and sputter as you're trying to drink it.
Back on Earth, water's ability to form a liquid skin is only slightly less visible. On a damp morning, trillions of water molecules cling together to create these droplets. This phenomenon, known as surface tension, also enables a water strider to walk on top of a pond, and beads of liquid to roll off the backs of these coots. Yet every day, surface tension's greatest role in creation is probably carried out here. Capillarity, the force that causes water to rise within a constricted space, is constantly at work throughout the plant kingdom. As water's surface tension and the liquid's attraction to a solid material, in this case the glass tube, draw the fluid upward. To illustrate this principle, the stem of a white carnation is split and placed into containers of colored water. The time-lapse camera accelerates our view of the process. If water was unable to creep upward, away from the pull of gravity, the chemicals and minerals plants must have to manufacture food would remain in the soil, eventually breaking the chain of life vital to most of the planet's organisms. How effectively can water be raised within a plant? Consider that for more than 2,000 years, capillarity and a host of other forces have worked to lift at least a ton of water to the top of each of these redwood giants every day. For rugged splendor and power, few places on Earth can rival Alaska's Glacier Bay National Park. Here, mountains of solid ice rise hundreds of feet above the sea, often calving or breaking away under their own weight. Nearly 3/4 of the world's fresh water supply is locked in polar ice caps and glaciers like these. And beyond their majestic presence, they stand as vivid examples of yet another unique property of water, vital to life on Earth. In the days when the milkman delivered his product in a glass bottle, freezing temperatures often produced an unexpected effect. Again, the time-lapse camera speeds up our view of the action. Milk is 87% water, and it's the water in the milk that has frozen and expanded. Almost any other substance, like this melted paraffin, whether solid, liquid, or gas, will shrink in volume as its temperature goes down, and as it shrinks, it becomes more dense. Water also shrinks during most of the temperature drop toward the freezing point. But below 40 degrees, something amazing happens. Water expands and becomes less dense. As it freezes into a solid, its density continues to decrease until it has finally gained about 9% in volume. This is the reason ice floats. It occupies more space than liquid water without weighing anymore. Since ice floats on the surface, it acts as a layer of insulation, protecting the water and life below from freezing. Now, if water acted like other liquids and became more dense when frozen, ice would sink, and more ice would be formed on the surface. In the winter, the rivers and streams would freeze and stop flowing. Lakes would freeze solid, and eventually, a disastrous chain reaction could cause even the oceans to become locked in ice. Warmer temperatures would melt only a thin layer of surface ice, forming a shallow slush. Lack of flowing water and intolerable extremes in climate would render the planet uninhabitable. But God created Earth to sustain life, and in his wisdom, orchestrated each detail necessary for survival. Daily, more than 10,000 thunderstorms explode across the planet, most of them releasing more power than a 100-kiloton nuclear bomb. A storm like this is one step in a cycle that results in the purification and distribution of the Earth's freshwater supply. This hydrologic, or water cycle, is an incredible machine. generating more power each day than man has been able to produce throughout the course of history. Let's follow its course for yet another glimpse of God's continuing care for the earth. To understand the water cycle, we must first look to its